Now let's take a look at problem 25 from chapter 6. It's a pretty interesting problem. I like it. And we have this sort of strange setup. We've got two blocks, one suspended, one's on a table. We have the coefficient of static friction here is given as 0.25. We've got this angle as given as 30. And it says that this chord is horizontal right there. We also know that block B, we have a weight for block B, and we want to find the maximum weight of block A in order for the system to be stationary. So we're going to be balancing out some things. Obviously, when it says the system's stationary and the maximum weight here, how heavy can this be? So when this pulls over here, it's going to barely equal the amount of friction that's over there. And the trick to this problem is actually that we're going to treat the knot as an object. And we're going to draw a free body diagram for block B, and we're going to draw a free body diagram for the knot, and we're going to go from there. So here's free body diagram for block B. Of course, we've got weight going down, mb times g. We've got a normal force going up. Ostensibly, those are going to be equal to each other because we're not going to have any acceleration in the up and down direction. We've got a tension going this way, and I'm going to label it T1 because we're also going to have a different tension over there, and then we're going to have a friction force going this way. And once again, just thinking ahead, this is going to have to equal this in order for the block to be stable. Or this is going to be just barely bigger than this when it's going to start to accelerate. So now let's draw a free body diagram for the knot. So there's the knot right there. I've got T1 pulling this way. So this is my chord 1 over here. I've got T1. Remember, tension pulls in two directions in the same rope, one from this side and one from this side. So that's T1. And I've got another tension over here. That's T2. And I could, if I wanted to, consider this as another tension down here. But just as a quick aside, if I draw a free body diagram for block A, I've got mass of A times G, and I've got this tension over here. Oh, there goes my lights. I got to turn the lights on. Okay, so once again, I've got this tension, this one right here, and this A, but those are going to equal each other. So I'm just going to call this force that's pulling down here on this knot, I'm just going to call that MA times G, which, by the way, is given in the problem as block B. Where's block A? Oh, no, we're trying to find that. We're trying to find this. This is our unknown. So all of these things are stable, which is pretty interesting. And now when you see something going off at an angle like this and you're given an angle in the problem, your job is going to be to break things up into components. So I think what I'm going to do is I'm going to erase this because it's kind of in my way. And I'm going to just rewrite it over here, MA times G. That's this force going down. That way I can actually work in this space over here. And I think I'll use a different color. So we have this T2 going to get broken up into components like this. So this is going to be T2 sine theta, and right there is going to be T2 cosine theta. All right, so now we can start to see how things are going to go together. What we know is that this T2 sine theta has to equal this weight right here. This is the thing that we're going for, because in this up and down direction for the knot, these two things are going to be balanced. So I could be more formal and write net force equations, but what I'm going to just kind of keep track of things. I know that T2 sine theta is going to equal MA times G. That's what we're looking for. We know the angle, so if we can find T2, then we are in business. So how are we going to find what T2 is? Well, we're going to need to look in a different direction. So now what I also know is that this force here, T2 cosine theta, has to balance out T1 because this knot is stationary, it's not moving. So let me write that down just in a separate spot. I know that T2 cosine theta equals T1. Remember, if I can find T2, then I can find what this is because I know the angle. So now if I know T1, then I can find T2. So how am I going to find T1? Well, looking back over at this one, I know this friction force has to equal T1. So let me write that down. Friction force equals T1. And the friction force, of course, is mu times the normal force. And just looking at this, the normal force is going to be this. These two have to balance each other out. So I can get mu B times G is going to equal T1. And now I've got all these pieces of information. I've got MB times G because that's the weight of, where is it? The weight, here it is right there. That's 711 newtons. I've got mu, which is 0.25, and I know, oh, this is right there. So I can find T1, plug T1 in here, I can find T2, and then plug T2 in here, and then I can find what this is right there. So it's a cool problem. You know, in the end, it's really not that hard, but just thinking about using the not as a separate object, I think is kind of the tricky one there. And I'll just leave you all to figure out how to plug in the numbers and get what you want. But this is the tricky part behind it. So there you go.